Hunting for the Rosetta Stone of neutrino physics. 70 years after their discovery, neutrinos remain one of the most mysterious particles in the universe. These ghostly entities barely interact with anything at all, making them extraordinarily difficult to study. Each second, about 70 billion neutrinos from the Sun reach every square centimeter of Earth, and they pass through the whole planet almost completely unaffected. Understanding these elusive particles could unlock some of the deepest secrets of the cosmos. Physicist Bernhard Schwingenheuer of the Max Planck Institute for Nuclear Physics in Heidelberg is one of the scientists leading the charge. At the heart of this quest lies a deceptively simple question. Is a neutrino its own antiparticle? Most subatomic particles have a distinct antimatter partner that can be identified by their electric charge. The electron has the positron, the proton the antiproton. But neutrinos carry no electric charge, which means they could be identical to their own antiparticles. If so, they would belong to a rare theoretical category known as Majorana particles, named after the enigmatic Italian physicist Ettore Majorana. If neutrinos are Majorana particles, it would help explain two of the biggest puzzles in physics: why neutrinos are so extraordinarily light compared to other particles, and why the universe contains more matter than antimatter. Without the latter imbalance, everything would have annihilated in the moments after the Big Bang, and we wouldn't be here. The best experimental test of this idea is to search for what's called neutrinoless double beta decay. In ordinary double beta decay, two neutrons in a nucleus simultaneously transform into two protons, releasing two electrons and two antineutrinos. In the neutrinoless version, the antineutrino is absorbed back into the nucleus rather than escaping. This is possible only if neutrinos and antineutrinos are one and the same. The key experimental signature is clean. The two emitted electrons carry away the full energy of the decay, producing a sharp peak in the energy spectrum. The LEGEND experiment buries sensitive germanium detectors deep beneath Italy's Gran Sasso Mountain, shielded by kilometers of rock from the cosmic radiation that would otherwise swamp the signal. The experiment will be sensitive enough to detect a decay so rare it would take, on average, far longer than the entire age of the universe to observe in a single atom. If funding falls into place, the full experiment is planned to begin collecting data around 2030. The technologies and materials developed for LEGEND will also help other fields, such as quantum computing and environmental monitoring. The discovery of neutrinoless double beta decay would be transformative, a Nobel Prize-worthy moment that reshapes our understanding of matter itself. The search, as Bernhard Schwingenheuer and his LEGEND collaborators know well, is just getting started.